So Jean Alam will talk to us about a very interesting subject of large Eddy simulations
Turbo machinery.
in turbo machines. In the laboratory, he's the guy in acoustics that does not really acoustics. Yes, sorry, actually I forgot the questions for Hugo. I was thinking about the panel discussion, so I didn't ask you, but is there any question for Hugo before we start the next presentation? Maybe in the Zoom meeting, Simon? Nothing yet? Okay. Okay, so we'll actually move to the last presentation before the break. And so I leave the microphone to Jean.
So thank you, Loic. Hello, everyone. My name is Jean Alam. I'm a PhD student in the beginning of the third year within the chair Arena between École Centrale de Lyon and Safran Aircraft Engines. And I'm going to present you an overview of my works in the PhD that is entitled Large Eddy Simulations for the Prediction of Fan OGV Broadband Noise. So I begin to present the context of the study. So it's well known today that the fan OGV stage of an aero engine, so it's the first part of the engine visible here, and it's the part that is visible when you're going up into an airplane, is one of the main contributors to the aircraft noise, like Hugo just said. This will become more and more important with the next generation of aero engines due to increased fan diameter in order to improve the efficiency of the engine and due to reduced rotation speed. At approach condition, so when the airplane is close to the landing, to the population, the broadband noise component becomes a major contributor to the fan OGV noise, stage noise. And that is generated due to many mechanisms schematically presented here in the left figure. So here we have a cross-section of the fan OGV stage. So we have the fan or the rotor blades, so the rotating blades, and the OGV behind, so it's here behind the fan. We have some OGV or stationary vanes, so what I will be calling the stator. And what are the mechanisms that generate what I call the broadband noise? I will note them here. For example, we have the interaction of the upstream turbulence or the turbulence in the boundary layers of the shroud and the hub with the rotating blades, so with the fan. We also have the tip gap noise that is generated due to the tip vortex generated in the tip gap region here of the rotor. And we have the two main mechanisms that will be studied in this PhD and that are also schematically presented here in the right figure, that are the rotor-stator interaction noise or the turbulence interaction noise that is generated due to the interaction of the turbulence in the rotor wakes with the leading edges of the stator, and the self noise or the trailing edge noise that is generated due to the diffraction of the turbulence in the boundary layers at the trailing edges of the rotor and the stator. So the objective of this PhD is the predictions of these two main noise mechanisms, so the turbulence interaction noise and the trailing edge noise of a fan OGV stage using large eddy simulations. So we are solving the large scales of turbulence and we are modeling the smallest and most costly to solve scales. For that, two phases were conducted. So the first phase is dedicated to academic configurations, so to flat plates, where comparisons with analytical models were possible. In this phase, a parametric study was performed in order to obtain, that allows us to obtain the numerical requirements in order to perform a well-conducted LES with a wall low, so we are modeling the very close, the boundary layer very close to the walls in order to reduce the computational time. These results were presented last year at the European Turbomachinery Conference, and the corresponding paper were selected between the top 10 in the conference and was directly published in the corresponding journal. The second phase is dedicated to the ECL5 ultra-high bypass ratio fan OGV stage designed at École Centrale de Lyon. In this phase, we have started by performing a pre-dimensioning tool for the LES in turbomachinery. that is based on the results of the parametric study in the phase 1. Then we performed some runs calculations for different operating points, and what I will be presenting now are LES configurations on LES calculations, let's say, on 3 different configurations that I will be describing just right here. So here we have the 3 configurations. So I begin by the figure to the left to have what I will be calling the full span 360 degrees LES. So it's a calculation on a full stage, fan here in the rotor in blue, stator, so the OGV in green. So we have the fan OGV stage, and the calculation on this stage will be so-called the full span 360 degrees. In order to reduce the computational time, we can take a periodic sector of this stage, like it's presented here in the middle figure. And doing so, we take one blade passage, and we impose some periodic conditions on the lateral sides, and the corresponding case will be called the full span sector LES. For a further reduce of the computational time, we can take a radial slice of this periodic sector at a certain height, like it's shown here. And doing so, we obtain the right figure and the radial slice sector LES. In this PhD, we have started by the radial slice sector, then by the full span sector, and finally we're now starting by the full span 360 degrees LES calculation. And by doing so, we are increasing progressively the complexity and the computational time of our simulations. So after I have presented the context and the objective of the study, I will be presenting some LES setup and results of the phase 2 dedicated to the ECL5 machine, and I will begin by the radial slice case. So I begin here very quickly to present the numerical setup. So the code the solver uses is AVBP. We are dealing here with a radial slice that is at 80% of the height of the machine, and that is 10% of the original span. That makes 10% of the original span in the span-wise direction of a periodic sector. The operating point is a partial regime point, is at approach condition, so 55% of the nominal speed. The numerical scheme is TTGC, third order in time and space, and NSCBC boundary conditions are used at the inlet and outlet sections. I note here that we are using, for this case, wall-resolved LES, so we don't have the wall model. And I finally show here a mesh of the view around the rotor and the stators. And we can note the mesh refinement zones. So we have the near wall refinements in order to well predict the boundary layers. We have the wake refinement, and we have what I'm calling here the upstream and downstream refinements, in order to well predict the acoustic waves up to and down to a certain distance, upstream the rotor and downstream the stator, because in this work we are going to make direct predictions of the noise. So the only result I will be showing for the radial slice case is presented here. So here we have a cross section of the fan blade. We have the fan here in white. Around the fan, we have the turbulent structure. So I'm presenting the turbulent structures colored by the vorticity. And in parallel, we have contours, Satinus contours of the dilatation field that allows us to observe the main noise sources in this configuration. So we can notice by the front waves that we have 2 main noise sources. So we have the classically studied trailing edge noise generated due to the scattering of these structures at the trailing edge, and an additional source noise that I will be calling the separation noise, that is generated close to the leading edge of the rotor, and we have seen that is generated due to pressure fluctuations close to the leading edge that are interacting with the walls of the blades and that are so generating this noise. And these pressure fluctuations are generated because of a recirculation bubble that appears in this region, and that is due to high incidence angles because like I have just said, we are working with a partial regime, very low speed, rotational speed. So now I pass to the full span sector LES. Here we have the same numerical setup. I will only note that we are now using wall-modeled LES. And what I'm showing here at the right figure are the turbulent structures around the rotor blade and the stator vanes, always colored by the vorticity. What we can see is that we have a very good transition of the boundary layers. all along the span, where fine structures can be observed, thanks to the well-refined mesh in these zones. I pass now to the main noise sources. So we have here a cross-section of the fan OGV stage at a height of 80%. So around the rotor at the left and the stators at the right. And we are also seeing the sources using the contours of the dilatation field. So what you can see is that we have two main noise sources. So we have the rotor-stator interaction noise that is generated at the leading edges of the stator. And we have the trailing edge noise that is generated at the trailing edges of the stator here and the rotor here. I just want to note that the separation noise that we have seen for the radial slice case is negligible in this case because we have taken adapted inlet conditions in a way to minimize this noise thanks to a study we have done on the radial slice case. In addition to some 3D effects that also are more present and more important in this case and that also reduce the separation noise. Now the idea is to be able to compare the acoustic predictions directly from the LES to some LES-informed analytical models. So for these models, we have used our LES in order to extract the flow, mean, and turbulent properties. These data extracted are used as input for the models. So here we use Hansen and Poisson's model. So that allows us to predict analytically the far-field acoustic power based on the LES numerical inputs. So here we have the comparison for the sound pressure levels at the intake section at the left and at the exhaust section at the right. We have the LES direct predictions in blue and we have the models in red and yellow. I'm not gonna go into details here, but I want just to say that, like we can directly see, we have a good agreement between the LES predictions, direct predictions, and the analytical models. And we can also notice that we have some under prediction of the noise by the models that may be due to some additional noise sources present in the LES but not considered by the models, like for example the tip gap noise that usually have an effect at low frequencies where the highest discrepancies can be found. I pass now to an introduction on the full stage, so the 360 degrees calculation. So using all the results of the parametric study of phase 1, we can impose the numerical parameters that allows us to obtain the physical requirements we need in terms of cutoff frequencies for the acoustics and for the turbulence spectra, and in terms of boundary layer refinements. So here we have the non-dimensional wall distances. Using the pre-dimensioning tool, LESCOT, that we have performed, we can obtain the mesh size and properties in each zone of the domain, and we can obtain the global mesh characteristics that are showed here. So in this case, we have a mesh of 1.5 million points that contains all the element types and connectivities, and it's a unstructured mesh. And that corresponds to about 20 million CPU hours. That justifies our price demand for this year of 30 million CPU hours, and that has just been accepted a few weeks ago. So finally here I am presenting the turbine structures around the rotor blades, always colored by the vorticity, for a full span, full stage, so 360 degrees LES, but on a coarser mesh that will be used for initialization of the refined mesh. I'm sorry. Oh, I hope you heard before. Now for the conclusions. Yeah, so I've talked about calculations, LES calculations on the phase 2 dedicated to the ACL5 ultra-high bypass ratio fan OGV stage. So we have 3 configurations. I talked about the radial slice sector, where we have seen the apparition of a recirculation bubble, and we have studied the associated separation noise. We have seen a full span sector LES where we are doing some comparisons with analytical models. And we have just begun by a full span 360 degrees LES. So I just note that it's a first of its kind calculation in LES for acoustic predictions. In the perspective, so for the full span sector LES, we are going to continue on study recordings and do some comparisons with runs calculations that we have performed. And for the full span 360 degrees LES, we are going very soon, I hope, to begin the computation. So just a few words here for the master students. If you are interested, we have a master thesis research project proposal in the same subject. So thank you for your attention. I would just like to thank the organization group, all of you for being here, and the ones that came just for this presentation.
Thank you, Jean. Thank you for your presentation. Is there questions for Jean? Maybe, you know, I had the chance to do my master degree in Lyon, so all of the researchers almost were my professors, so it can be a bit my vengeance here and say, Didier, do you have a question maybe, or or maybe Christophe can have a question too.
You can also, but not very hard.
We have a question there, Jean. You just saved them.
The week is not.
Thank you so much indeed for this nice presentation.
Thank you.
And I just wanted to know that what is the difference between the time computation between the radial slice computation and the full span? Do you have any idea?
In fact, yeah, in fact, here what I've presented, there's not a big difference. Why? Because the radial slice was performed for war resolved LES. So I had really a mesh with y plus lower than 1 at the walls and x plus and z plus very, very, very low. So, and for the full span case, it was with a wall model. So you see, but like if we want to say they were comparable. But if you want to compare, like I've done also some wall modeled in the radial slice case, and if you want to compare, there's about 10 times or no, even 10 to 15 times difference. If we were comparing wall modeled radial slice with wall modeled full span periodic sector, yes.
Thank you, Jean, for your answer. Is there another question, maybe? Okay, so Simon, no question in the Zoom. Okay, so thank you again, Jean. Thank you for your presentation. We can thank Jean for everything.